Welcome to this explainer. Okay, so today we're diving into something that literally separates the junior developers from the seasoned architects in system design interviews. We're talking about why just quoting the famous CAP theorem might actually be a huge red flag, and why a framework called PACELC is what you really need to be focusing on. Let's get right into it.
You know the quote. We've all heard this classic rule of system design, right? It's repeated in every textbook, it's scattered across engineering blogs, and you'll hear it echoed in whiteboard interviews everywhere as this ultimate, unbreakable law of distributed databases. Just pick 2 out of 3. It sounds super simple, elegant even. But here is the secret. That framing, it is a complete trap. If you sit down with a hiring manager and confidently declare that you just pick 2 out of 3, you're instantly signaling that you are designing for a whiteboard in some perfectly sterile room, not the messy reality of production systems.
Section 1. Busting the CAP Theorem myth. Let's start by looking at what CAP actually says, and why the way we usually talk about it is just fundamentally flawed.
Formulated by Eric Brewer way back in the year 2000, CAP defines 3 properties. Consistency, which means all nodes see the exact same data at the same time. Availability, meaning every request gets a response. And partition tolerance, which means the system keeps running even if network links drop. The theorem highlights the impossible choices we face when a network link breaks between replicated database nodes. But, our understanding has evolved quite a bit in the last 2 decades. And here is exactly where that whole pick 2 myth completely falls apart. See, the myth implies that you can just choose to not have partitions. But in real-world distributed systems, network links break. It is inevitable. You cannot choose to avoid network partitions any more than you can choose to avoid earthquakes. Because partition tolerance is a mandatory reality, you aren't actually picking 2 out of 3 at all. So the crucial takeaway here is that when a partition inevitably happens, you only get to pick one of 2 options. You either refuse to respond to ensure correctness, which gives you a CP system, or you return a potentially stale response. Returning data that might be a few seconds out of date just to keep the lights on. That gives you an AP system. That right there is the actual CAP trade-off.
Section 2. The missing normal operations. Because even if you frame CAP correctly, it still has a massive blind spot that ignores day-to-day reality.
Think about it. CAP only describes the 1% of the time the network is actually broken. But astoundingly, it tells us absolutely 0 about the 99% of the time when the network is perfectly fine. For the vast, vast majority of your system's lifespan, there simply isn't a network partition.
So what trade-offs do you actually make when the network is working flawlessly? Because even when those network cables are perfectly intact, the very act of replicating data across multiple nodes forces you into a constant, everyday trade-off. It's a fundamental pull between speed and correctness that CAP is completely 100% silent on. Section 3, enter PACELC, the full picture. This is exactly where the PACELC theorem, which was introduced by Daniel Abadi in 2010, comes in to fix CAP's massive blind spot. It provides a much more complete mental model. Here's how this framework builds. The first half is exactly what we just covered. If there is a partition, that's the P, you choose between availability or consistency. But the absolute breakthrough is the second half. Else, meaning during normal operations when everything is fine, you must trade off between latency and consistency. PACELC. That else half perfectly captures the trade-off senior engineers make constantly. If you want strong consistency, you literally have to wait for your writes to sync across multiple replicas before you can confirm the action back to the user. That unavoidably adds latency to your system. Or, alternatively, you can acknowledge the write immediately to get that sweet low latency, but you have to accept eventual consistency, basically accepting that some users might briefly see stale data. Section 4. Mapping real-world databases. When you step into a system design interview at a FANG company, this PACELC framework is exactly how hiring managers expect you to evaluate database choices. What's really fascinating here is how every single major distributed database falls perfectly into these operational categories. Instead of just blindly memorizing names, you can instantly understand a database's core philosophy just by looking at its PACELC classification. Let's break these down, starting with PA/EL. Systems like DynamoDB, Cassandra, and ScyllaDB live here. They optimize for single-digit millisecond latency and absolute availability. They're the high availability no matter what family.
That makes them absolutely perfect for high-throughput things, like, say, gathering temperature data from millions of smart thermostats in IoT telemetry, or maybe storing user sessions where a slightly stale read isn't going to break the application.
Now, on the exact opposite end of the spectrum, you have systems like Google Spanner or HBase. These are PC/EC databases. They guarantee strict global consistency above all else. They're designed for use cases where stale data is simply disastrous. Think of a financial ledger tracking bank balances. You definitely don't want eventual consistency there. But, you do pay the price for that absolute correctness with higher latency.
And then right in the middle, you have the compromise. MongoDB and its default configuration is a fantastic example of a PA/EC system. It essentially tries to have it both ways. It favors consistency in normal, everyday operations, but brilliantly pivots to prioritize availability if a network partition suddenly isolates the primary node.
Section 5, Designing for the Business. Because ultimately, understanding PACELC is not just about memorizing some academic acronyms. It's about translating real-world business needs into technical constraints. Think about it like this. A social media feed needs to be lightning fast and always online. If a user's like count is a few milliseconds out of date, honestly, no one cares. Well, unless maybe you're a massive influencer. That makes PACELC a perfect fit. But an e-commerce checkout system, it absolutely cannot accidentally oversell physical inventory. Correctness is strictly required, which demands a PCEC approach. So if you want to sound like a senior engineer in your next design review or interview, follow this exact structure. Don't just rattle off a list of technologies. Name the specific trade-off using the PACELC framework. Tie that trade-off directly to the business requirement. Make your consistency choice explicit. Only then should you name a specific database that fits. And crucially, always acknowledge the downsides of your architectural choice.
Because at the end of the day, CAP only tells you what happens when the network breaks. PACELC tells you what trade-offs you're making every other day of the year. So the next time you sit down to architect a distributed system, you have to ask yourself, are you just quoting letters on a whiteboard, or are you truly designing for the reality of the business? Keep that in mind, and you'll be building systems that truly scale. Thanks for joining me on this explainer, and I will catch you in the next one.